Okay, thanks everyone for sticking out for so long. I'm here to present my paper on dynamic costs of research shocks in collaboration with Paul over there, evidence from Cape Town's water crisis. Now, the motivation of this paper is quite simple. In the past several decades, we've observed several major cities across the world that have faced acute temporary water shortages. Now, cities are quite special because they have a few features we think are interesting for studying this question. First, they have a supply that is relatively fixed in the short run. It's not easy to increase the supply of water, and if we want, we can speak about that a bit later. But the second is that they have essentially two claimants for water. They have households and they have firms. And households use water for some direct consumption benefit through drinking, sanitation, showering, watering your garden. And firms use water as a critical critical input into production, and this provides employment and wages to the households. Now, if we frame this as a problem where there's the local policymaker who faces some supply constraint and therefore has to attenuate demand, they are either implicitly or explicitly making some allocation decision between households and firms. Now, as economists, we would think, well, let's set the price of water at whatever clears the market, given the supply that we have. And this would be efficient in case there are no externalities or market failures on either of these two uses. But we think both of them are actually facing different externalities that make this problem a little more complex. So on the household side, you can obviously think that if we go below some subsistence amount of water, we're going to face some public health externality. And instead, on the firm side, we think this is a bit more interesting and less studied. That is that firms don't exist in a vacuum. So firms exist in networks, they have spillovers onto each other, they provide agglomeration forces into the economy, and therefore we also need to account for those when we design water allocation policies. And currently we see a variety of different solutions being adopted across the world, from prices, quotas, physical restrictions that haven't fully incorporated what these potential effects are, and therefore we don't really have an idea of the economic costs. So the research question is going to be deceptively simple. How should cities allocate water between households and firms when they're facing a drought? So some temporary resource restriction. And we're going to take advantage of Cape Town's drought between 2016 and 2018 that generated this one-year water crisis in the city to try and answer this question. Now, to give you a preview of what we'll show you today, on the production side, so on the firm side, 6 years after the drought ended, so last year, essentially, firms that are in water-intensive sectors are smaller than they were prior to the drought, and there are a few of them. So on average, these sectors are about 20% smaller, and this seems like a persistent effect. Moreover, it's being driven mainly by firm exits, and those workers that lose their jobs are not becoming re-employed in the long run. And the other finding we think is interesting and that will motivate the model that we'll show you is that these losses tend to be concentrated spatially. So there are locations within the city that had water-intensive production, and these are the locations that are losing firms and are losing employment. And moreover, these losses are spilling over to non-water-intensive firms in the same locations. So it really seems like it's something happening at the location level that are leading to these persistent losses. All that to go back to the discussion Bruno and Sean were having before, we're then going to have a model that is going to try and incorporate these externalities to try and generate the cost that we're seeing when determining what other allocation policy could have been used in the face of the drought to try and minimize these long-run costs. Okay, so in terms of the literature, I'll be very brief. Obviously, there's many strands of literature that we're touching upon. We want to try and show how some of the, not only the climate shocks, but also the policies that are adopted in response to these climate shocks can have persistent effects. And that will tie neatly into the sort of spatial argument that we're going to try and make, showing you how we can have these potential tipping points and de-agglomeration effects in the economy. And that will then feed into our model on how should we optimally allocate these resources under scarcity. Okay, so let me tell you a bit about Cape Town's drought. For those of you that maybe know the literature, a little bit. It was a massive drought that hit the city of Cape Town starting in 2015, 2016. And these two photos are taken from the exact same location 1 year apart. So this is the biggest reservoir in the city of Cape Town. It provides about 60% of all drinking water to the city. And this photo was taken at the peak of the drought in January 2018. And this photo was taken 1 year later, once the rains had returned, and essentially the whole water market had been normalized with prices returning to prior trends. And I'll show you a bit more of that in a second. So we're really talking about a massive climatic shock and very extreme policy response that I'll explain in a second. So how does the water market work in Cape Town? It's a fully vertically integrated municipal provider. So the city controls everything from the construction and maintenance of these reservoirs to the distribution to the billing of the households. And at least at the time of the drought, it was an entirely rain-fed system with some minimal groundwater extraction. So essentially, the city has exclusive rights over some rainfall pluvial basins that they collect the water for and then distribute it to households. And the drought then happened, which I can't explain the meteorological science, but essentially this tail event where three separate phenomena occurred at the same time that led to 3 years of historically low rainfall. And for this reason, the city essentially ran out of water and had to put in steep price increases to curb demand. So to give you a bit of an idea on timing, the drought began in late 2015, early 2016. However, the strong pricing responses, and it was mainly a price response, and we think this is important, only began in December 2016 and then expanded through 2017. So in all the results we'll show you today in our event studies, we'll be using 2016 as the base year, essentially the last year of economic activity that was unaffected by these large price increases. Then importantly, the rains returned in June 2018 and all restrictions were eased within a few months. Yes.
To Bruno Nishan's points earlier, so that's a backwards looking worst drought in recorded history, and we're seeing a lot of worst effects in recorded history. Just in thinking about kind of dynamic changes they might make, do you know anything about how much more prevalent something like this is going to become?
So in the case of Cape Town specifically, no. In the sense that the climate scientists, or at least the things I've read in the literature, don't think they're learning anything new from this specific drought. So it's really just this tail event of these three phenomena occurring at the same time. There's a 150 to 300 year return period for that happening again, and this hasn't been shortened, or no new information has been learned. In terms of motivating the paper, this is definitely part of it, that we think this is going to be a phenomenon that occurs more often in different cities across the world, and so it's very important to try and understand how to allocate water. Okay, I'll also add one thing to that I'll touch upon later. The political salience of the event led the city to diversify its water sources. So also in terms of the expected desalination plants in place, so that should be in some way attenuated.
Household behavior?
We'll get to that in a second. Okay, so let me tell you a bit about the response, the policy response of the city of Cape Town. There was messaging, but there were no restrictions in terms of how you could use water. It was purely a pricing response. So if you're willing to pay, you could use water. Now, the firm side is relatively easy. It's a flat price per kiloliter of water. And they increased this initially quite slowly throughout 2017. And then when the rains really never returned for the third winter in a row, they put a quite steep price increase. So the price of water for firms increased by about a factor of 4 or 5. As soon as the rains returned, they decreased it. Okay, so this is going to be the main shock that we're going to be taking advantage of. Now, the household side is a little more complex. They have these increasing block tariffs. So think about your marginal tax brackets. The more water you use, the more you pay per liter. And so I will just plot the 25th, 50th, and 70th percentile of average water expenditure per kiloliter from households. It follows a similar pattern to firms. Obviously, the intention is that lower users should pay less, and this is reflected in the average prices that we see. there were highly punitive rates for very high users on the household side to try and punish people refilling pools with drinking water, essentially, and this is what it looks like at the 95th percentile of consumption. Okay, so what actually happened to consumption, to cut to the chase? The bulk of the reduction in water use came from the household side. So domestic users really decreased their water consumption in response to these very high rates. Water consumption of households fell by about 70%, the peak of the drought. On the commercial side, there was some mitigated response and decrease, and I'll tell you a bit more about that in a second. Yeah,
Right, was one of the lines on the previous slide the firm price? This is
the purple one is the firm price.
So they just have like a way lower elasticity, I guess.
They have a way lower elasticity, and I'll also show you a bit more about where that's coming from. And for those of you that have seen Kelsey Jack's paper on dodging day zero and a few other papers by Martin Bissier on this, it really seems that on the household side there was both some adaptation in the sense of changing your faucet to lower consumption ones, plus on the higher income side they dug out bore wells to use up more groundwater. And there were large behavioral changes in the style of sort of Costa Gerard, where once you get used to using less water during the peak drought, you continue using less water. And for that reason, we don't really see this return to pre-drought levels. Whereas what we really don't have a lot of evidence on is what happened to firms. Because also on the firm side, we see a reduction in water use, and it doesn't pick up again. And so there's really a question of this, is this an intensive response that firms have changed production technology somehow and they're able to use less water, or is there some extensive margin response? And so to give you a very quick preview and zoom in on the firm side of the water use, we see that a large chunk of the decrease in water consumption of firms came from firms exiting the city or production all overall. So survivors did decrease consumption a small amount, about 10%, but the largest share of the reduction came from firms exiting. And this is exactly the kind of motivating fact that is leading us to delve into the firm side of the model a lot more, and what we're going to show you for the rest of today. Okay, so having motivated that, we're going to have 5 empirical facts about what's happening on the production side of the market. And to do that, we've had to collect a lot of data. Now, this was a highly long and painful process, as some of you know, but at the end of the day, we managed to secure what I think is a lot of really valuable data to try and answer this question. So from the Treasury in South Africa, we have the universe of formal employment, employee-employer match. So we observe all the standard things you would expect from the data. So on the worker side, who they work for, how much they earn, their industry, where they live and where they work. And on the establishment side, we see who their employees are, revenues, profits, employment, industry, and whatnot. Then from the city of Cape Town, we managed to get access to the universe of utility data. So we have geolocated every single water meter in the city. So both for households and for firms, we know exactly where the water meter is and how much they're consuming at a monthly level and how much they are paying for that water. And we can tell if it's a commercial user or a residential user because of the tariff they are on. Now, in an ideal world, we would be able to match these. Unfortunately, we're not because of confidentiality reasons. And so our main measure of exposure will be whether your sector is water intense or not. So from Statistics South Africa, we got access to these input-output tables at the 3-digit sector level. And essentially what we're able to find is the percentage of expenditures that is on water for every sector in the country. And so we come up with 2 different measures of water intensity. One will be a binary measure, which is essentially the top quintile of sectors by water use as a percentage of expenditure. And then the second is just a continuous measure, which is the percentage of your expenditure that is in water. Okay. Our main empirical specification will be this triple difference specification. So the tax data that we have is for the whole of South Africa. And so we'll be doing essentially at the city year sector level, how do a variety of outcomes change when we compare water-intense versus non-water-intense sectors in Cape Town versus unaffected metro areas in South Africa before and after the drought, or rather for our event study year by year. Okay, and so now for our main set of results, the first thing that we find that is in line with those water findings that we had shown you before is that we have a persistent decline in water-intensive sectors in the number of employees and in the number of establishments in Cape Town after the drought. So here we're thinking about sector-level observations, those sectors that were most exposed to the drought in terms of their water consumption, and therefore were hardest hit by these price increases, observe about a 20 to 25% decrease in number of employees and number of establishments. And what was most striking to us when we started working on this is that this seems to be persistent. To this day, there is no, yes, here there's a tiny bit, but there's no signal of recovery in either of these measures. And so, having access to this great data, we said, let's try and understand what's going on both on the employee side and on the establishment side. So we're going to start with some firm dynamics in terms of the establishments. And the first thing that we looked at is exit. So we wanted to understand, okay, what are the exit dynamics here? Is it all happening in bulk, or is it some slow bleed away from these sectors in Cape Town? And what we find is that we have this increase in exit rates of about 6-7% occurring in these sectors immediately after the crisis, or essentially after the price increase. And then these settle back down to counterfactual levels after. So it seems like there's just some mass of exit occurring in response to these price increases. And similarly, if we look at entry rates, the triple difference of entry rates, again, it seems like there's some decrease in entry rates immediately after the water shortage or the crisis in Cape Town, but these also then converge back to counterfactual levels. Now, the one thing that we found interesting here and that explains this persistence is that we don't see these trends reversing to try and replenish these sectors. So it's essentially a massive exit, and then we go back to the same trend that before, but just at a lower level. And this is part of what's going to motivate the model that comes later. Okay, now if we move on from the firm side, and instead we look at the worker side, here we also have what we think are quite interesting findings. So as we said, we only have formal employment. So if we just run a linear probability model on the probability of being employed, having worked in a water-intensive sector in 2016, we see this decrease in the probability of being employed that actually diverges over time. So workers that were employed in water-intensive sectors in 2016 are less likely to be employed immediately after the drought, and this probability only decreases over time. And instead, for those who were employed in 2016 in water-intensive sectors and managed to remain employed, so conditional on being employed, their earnings are actually increasing. So I think there's a few stories for this, and we can't exactly tease out which it is. They're either selected on ability, and therefore the most able workers are being employed elsewhere and are being rewarded for that ability, or it's workers in the most productive firms that are remaining employed. We can come back to this, but we can't really tease out which of these two stories it is. And so now we've shown you what we think are aggregate city level results, but also we were really curious about what's happening at the spatial level within cities. And so again, we have a lot of this data from both the tax authority and from the utility, and we can't match firms and utility one-to-one, but we can match spatial aggregates. And so the next thing that we did is we used one of those spatial aggregates that we are allowed to export, which are these Uber hexagons that cover the city. So we have all the tax data that we can aggregate at these Uber hexagons, and we also can then match them to the utility data that we have. And so if we just do a very naive in a certain sense, water intensity of employment, taking the utility data and matching it to actual employment patterns across the city, we have this measure of water intensity at a spatial level. Okay, and so all that we're going to do here, we're showing establishments, but employment looks quite similar, is we're going to ask what happens to employment in locations that in 2016 were water intensive. And these are the findings. Again, very similar findings to before. Locations that were water intensive in 2016 find some decrease in establishments and in employment immediately, and this only diverges over time. So it's as if these locations enter some low equilibrium and they're not able to get out of it. Now, question that we had is obviously, is this just a mechanical feature of these locations having more water-intensive firms? We've seen that water-intensive firms are exiting, and therefore these locations suffer the most exit. And to try and answer this question, we try to understand whether there's any nonlinearity in exits depending on how water-intensive your location is. Now, please forgive me, the graphs I'm about to show you are very ugly, but to edit them, I have to go to South Africa, and it's not exactly easy, so work in progress. But essentially, we will show you what is happening to exit probabilities if in your location you have more water-intensive firms around you as a share of the total firms that exist around you. So we're trying to understand whether there's something to this nonlinearity or agglomeration story. And on the left panel here, we have essentially quartiles of water intensity of firms around you. And we see that exit rates spike for water intensive firms if they have a greater share of firms around them also being water intensive. Okay, so the same water intensive firm is more likely to exit if they are surrounded by other water intensive firms. Now, this is some nonlinear amplification that we sort of expected given agglomeration, but then the other finding that we didn't expect and that we think is very important is that this holds true also for non-water intensive firms.
And why you did not expect it?
Well, when we were thinking about agglomeration to begin with, we thought this would happen mainly within sectors. So we have some specialized suppliers, some thicker labor markets. For example, the steel industry was one of these that, yes, okay, if a bunch of the steel firms leave, also the other firms leave, but this might actually be positive for other firms that come fill these locations because of pricing responses. And actually, that doesn't seem to be the case. Other unconnected firms, or rather, we don't know if they're not connected, but firms in other sectors are also leaving. And then I don't have it here, but also entries depressed for both water intensive and non-water intensive firms in those locations.
What about input-output linkages? You're a non-water-intense firm, but you depend a lot on the firm that is exiting.
Good. So, okay, we haven't actually done firm-level input-output linkages, but we did do a version of exposure that is essentially the Leontief inversion of the input-output matrix. So not how water-intensive your own sector is, but how water-intensive your supply chain is. And the results look very, very similar.
How about ag demand? Because the households were also affected by through the thing. So maybe they change or shift demand to different sectors as well. And this can explain.
Good. So I have two questions to this. The first is that's part of what we want to try and capture with the model. The second is, and again, I don't know if I have this later, but we can come back to it if I do. We break this down by tradables and non-tradables. So especially export level sectors shouldn't be affected by any demand, and they actually have virtually the same effect. Okay. And so this leads us to what at the time for us was a bit of a puzzle, which is what mechanism can explain all of these findings? And we came up with a bunch of different things along the road. So the first one was, this is just a slow adjustment and eventually we'll come back to the same equilibrium, but we discarded that relatively fast because we really saw these trends diverging and no sign of recovery 6 or 7 years on. The second is, well, there's been some reallocation of economic activity to the survivors, And actually, what we're missing out in the establishments is this productive reallocation that the drought had. And actually, when we look at survivors and the average size of the survivors, we see no reallocation towards the survivors. So they have no increase in revenue, they have no increase in employment. They actually look exactly the same as counterfactual metro areas, if not worse. We then thought, well, maybe it's some story that it's these multi-establishment firms that are able to better reallocate production over space. It's sort of this Castro Vincenzi story of, I've learned something about the risk of a location, and so I'm able to reallocate across my plants. And actually, it seems like all the exit is driven by single establishment firms, and multi-establishment firms are not reacting at all. And so that led us to think, oh, it's more something about credit constraints or selection on productivity, and you'll see that coming into the model. And then the last thing that, also as Claire brought up before, it might be some form of information that firms are learning about a given location and its climate risk, or they're repricing the risk of operating in Cape Town. Now, for a variety of reasons, we don't believe this to be the case. The first is just the sort of climate explanation. This really was a tail event that we don't expect to be happening again in the short run. And at the same time, the city of Cape Town has diversified their water supply. And then we have a bunch of other evidence that tells us something that we wouldn't expect if this were purely a risk or information signal. For example, the entry rates going back to counterfactual levels, we would expect these to remain depressed if this were purely an information shock. We also would expect these multi-branch firms to be shifting away from Cape Town. And at the same time, we ran a placebo on other cities in the Western Cape. So this is the southwestern part of South Africa that was affected by the drought. And these other cities who didn't use a price-based instrument show no differential trends to the rest of South Africa. So this really seems like a Cape Town specific effect driven by some combination of the drought plus the policy plus whatever else we think is layered on top of that. And so the interpretation that we're going to use and that we're going to then build into our model is that these higher prices forced some of these smaller marginal firms to exit. This led to some erosion in agglomeration and some loss of these complementarities that existed in some locations, which made re-entry unprofitable and lowered, leading these locations to lower steady states. And so in the last 2 minutes, I will introduce the model that we think will be able to generate all of these results. So I tried to abstract as much from equations because I didn't have time, but essentially on the firm side, we're going to have a mallet style model where firms pay a price to have a productivity draw from a Pareto distribution. The worker side is going to be dynamic and it's going to respect this Caliendo-Dworkin-Paro type decision where they make some choice over sectors and locations and they face switching costs. And we're going to incorporate what we think is the potential for an externality in the water market through some stone gear, non-homothetic demand for water. And then that's going to be complemented by some locations that provide housing for workers. Do you have questions?
Is there migration happening?
There is no migration happening in the model at the moment. There are also, at least from our data for formal workers, doesn't seem to be any out-migration in response to this shock. And then the one feature that is able to generate this persistence, for those of you more familiar with the spatial models, is that we're going to have some lagged agglomeration term that enters the state space. And this is going to anchor some locations in future periods into a lower equilibrium. And without a big enough shock, you're not able to escape from this low equilibrium again. So that's going to be essentially the dynamic feature of the model. And then within the period, you'll solve for employment prices and then the Pareto cutoff. That's just some more on the intuition of the model. But essentially, the reason we want the model is to test various different allocation mechanisms, solve the full transition path, and therefore compute welfare as the net present value of the agency utility in the city to try and understand which allocation mechanism can reduce welfare losses from the drought, accounting for these costs that we think until now haven't been accounted for. And so just as a very quick takeaway, we think we provide some new evidence on how temporary water shocks and water pricing shocks can lead to some permanent effect on the production side of the economy, driven by the contraction of water-intensive firms, but also their spillovers on their non-water intensive neighbors. And if we account for these dynamic changes, we might have a different optimal allocation of water during the drought. That's all from me.